Hey guys, my name is Z and you're watching MakesItEasy. And welcome to my IGCSE chemistry series where today we have topic 8, which is energetics. And here are the lessons that I'll be covering in energetics. So we have calorimetry, energy changes, more calorimetry, delta H and bond energies, and more bond energies. So it's a relatively short topic, so check out the pinned comment for all the timestamps. But we'll move on now to calorimetry. So here's a basic setup of calorimetry experiment. We have a clamp over here, a test tube or a boiling tube, thermometer, burning food like mounted on needle or anything. And here are the control variables that we need. Like the control variables could be volume of water, the mass of the food, the distance from the food to the boiling tube because of the flame, and the thickness of boiling tube. And of course there's more control variables, but here are just some examples. And I'll move on now to more alcohol information. Alcohols are a family of organic compounds that contain carbon, hydrogen, and oxygen atoms. And the defining feature of an alcohol is the OH group. And we discussed this in organic chemistry. And we have methanol, ethanol, and propanol. And alcohols like ethanol and propanol can be used as fuels. So here's more alcohol. The difference between secondary, tertiary, and primary. Primary alcohol is when the carbon that the OH connects to only one other carbon. I see this, only one other carbon. But the secondary alcohol is that the carbon that the OH is connected to is connected to two other carbons. You see this? And the tertiary alcohol, the tertiary alcohol is the carbon that the OH connects to. Like let's say this, OH2 is connected to 3 other carbons. So it could be this, this, and this. So 3 carbons. So primary, secondary, and tertiary. Then we'll move on to more alcohols as a fuel. Alcohol is used as fuel because it is flammable. And for example, ethanol is an alcohol formed by the combination of ethene and water. As with most of the other alcohols, ethanol is flammable, so it will combine with oxygen fairly well to give off carbon dioxide and water as waste product in combustion. And this process is called complete combustion, as we talk about in organic chemistry. Like the different use of alcohol, like cooking we have ethanol, biofuels we have ethanol and butanol, and the spirit burners we have methanol. Then we have calorimetry experiment. I'll just skim through this. Like just measure the mass of the spirit burner over here with lid and record it, and take the temperature of 100 cm cube of water and record it, and light the spirit burner and leave it to burn for about 2 to 3 minutes, and replace the lid to extinguish the spirit burner and record the temperature of the water and measure the mass of the spirit burner again, so that you get the mass of the fuel used and the temperature change, and repeat it with 2 other fuels. And here's just a result table. We have the fuel of methanol, ethanol, and butanol. So we're trying to investigate the change in temperature of water and the change in mass of the fuel. So here's the setup. Then we have some energy content. The energy content of a fuel can be found using this equation. We have Q equals mc delta T. Q is the energy given out by burning fuel in joules. M is the mass of the water heated by burning fuel in grams. And C is the specific heat capacity of water, and it's 4.2 this over here. And delta T is the change in temperature of the water in degrees Celsius. And one thing to note is that the density of water is around 1 grams per cm cube. Then we'll look into the combustion of alcohol experiment, which was the one just now, calorimetry. So I investigated in ethanol, propanol, and butanol, like 2, 3, 4 carbons each, the starting mass, ending mass, to get the mass of change in alcohol. The volume of water is always constant. The starting temperature of water doesn't matter what the starting temperature is, because you're going to find the temperature change anyway. So starting temperature of water and ending temperature of water, they find the temperature change. And the energy, as I talked about, will be mc delta T, mass c delta T. And then you get this, the energy. So you can see it's constantly increasing. And the enthalpy, which is the joules per mole, you just have the joules over here and divided by the moles of each respective alcohol. So one thing to note is that you can see this, and they all have a negative sign because this signifies an exothermic reaction. Because if a product is increasing in heat, like the temperature increases, that means that the heat is being transferred to the surrounding, like giving out. That means that it's an exothermic reaction because exothermic reaction is heat being given out. But we'll focus more on it later. So you have to put a negative sign. Then we have some errors in calorimetry, some plenary. Calorimetry experiments are not very accurate, and a lot of the energy released by the burning fuel is not transferred into the water, and it is instead lost into the atmosphere. So you can have a read of the bomb calorimetry. Like we have the thermometer, lid, stirrer, and insulator jacket, and these. So move on now to energy changes. And as I talked about just now, exothermic is when a reaction increases in temperature, and endothermic is a decrease in temperature. And you can think of it this way: from a gas to solid is exothermic, because we know that gas particles have the most energy because it's constantly moving in random directions, like random movements, and they're like in the air, so they need lots of energy. But solid, they have a fixed position and fixed state, so the particles don't have much energy. So from gas to solid, the energy has to be given out because it's going from more energy to less energy. So this energy being given out is in the form of heat energy, so it's exothermic reaction, and the enthalpy decreases. And from solid to gas, vice versa, it's basically from low energy to high energy because gas particles need energy. So the solid takes in the energy, so it's endothermic because it's taking in the energy, and the reaction will decrease in temperature, and enthalpy increases. And enthalpy is this is a complicated description. It's a sum of the internal energy and the product of the pressure and volume of a thermodynamic system, and it's the amount of internal energy contained in a compound. But we'll focus more on enthalpy in a minute. Then we have exothermic and endothermic. Exothermic reactions release thermal energy or heat into their surroundings, and exothermic reactions can occur spontaneously, and some are explosive. And some exothermic reactions include combustion, respiration, neutralizations of acids and alkalis, reactions with metals and acids, and the thermite process. And endothermic reactions absorb thermal energy and so cause a decrease in temperature. For example, the example could be thermal decomposition, like calcium carbonate in blast furnace, photosynthesis, some types of electrolysis, and this right here. Then we have some reactions to determine if it's exo or endothermic. Like we have sodium hydroxide plus dilute hydrochloric acid, the equations, temperature before and temperature after. You can see the difference is a positive temperature increase, so it's exothermic because it's giving out heat. For this, you can see the temperature decreases, so it's endothermic. And copper 2 sulfate solution plus magnesium powder, you can see the temperature increases, so it's exothermic. And sulfuric acid plus magnesium ribbon, it's exothermic. So there tend to be more exothermic reactions than endothermic reaction. So now we have some questions. The first reaction is between an acid and an alkali. What do we call this type of reaction? And it's called a neutralization. And what gas is given off when sodium hydrogen carbonate reacts with citric acid and it's carbon dioxide? Because it's here, get CO2 gas. And which type of reaction takes place between copper 2 sulfate and magnesium? And it's a displacement reaction, and it's an exothermic reaction. Because you can see this, the magnesium displaces the copper in the CuSO4. And which reactions are exothermic and endothermic, and we talked about it just now already. And describe in terms of bond breaking and bond making why some reactions are exothermic and some are endothermic. And in exothermic reaction, the bonds are forming because liquid and solid are formed. And in endothermic, the bonds are breaking because liquid or gas is formed. And gas atoms have the most energy because they are constantly moving around. So remember that exothermic is bonds forming, endothermic is bonds breaking. Then here's energy changes for activation energy. Reaction takes place when particles collide with a certain amount of energy. And the minimum amount of energy needed for the particles to react is called the activation energy, and it's different for each reaction. And the rate of reaction depends on two things: the frequency of collisions between particles and the energy with which particles collide. And if particles collide with less energy than the activation energy, they will not react. The particles will just bounce off each other. Then we have some energy profile diagram for energy changes, as we talked about activation energy just now. So it's a key part of this energy profile diagram. You can see this exothermic reaction and endothermic reaction. And the x-axis is reaction progress, and the y-axis is potential energy or enthalpy or energy. And in an exothermic reaction, the ending energy will be less than the starting because energy is being given out. So exothermic is going down and endothermic is going up. And you can see the different energy release and activation energy here. And here's epsilon is going down, so it's exothermic. And this H right here just means enthalpy, and you can think of it just like energy. And here you put the reactants, and here you put the products. Then we have enthalpy. The unit for enthalpy is joules per mole, J/mole. And enthalpy, or H, is the total kinetic and potential energy of a system at a constant pressure, and it's the energy change per mole of fuel burnt. And the change in enthalpy is the change in the heat of a system, and delta H equals H final minus H initial, like this. And as we talked about just now, exothermic reaction is negative enthalpy, and endothermic reaction is positive enthalpy. Then we have this principle right here. It's quite a complicated principle. And it says that when the stress is placed on the system at equilibrium, the reaction will shift to counteract the effect of the stress in order to return to the equilibrium. So basically all reactions want to be in equilibrium, but there are four variables that can change an effect of a system at equilibrium. It's these four. So when these four affect the equilibrium reaction, and it becomes not equilibrium, the reaction will always try to become equilibrium. So this could be concentration, pressure, volume, and temperature. And you can have a read of reactions shifting towards the opposite side, the right or the left. And when we say the reaction will shift right, this means that the forward reaction is favored and will happen at a faster rate. And the concentration of the products will increase. And when we say the reaction will shift left, this means that the reverse reaction is favored and will happen at a faster rate. And the concentration of the reactants will increase. But we'll look more into this in the reversible reaction lessons in our next and our last topic of chemistry, which is equilibrium. So we'll move on now to experiment setup and displacement reaction. And here's a planned experiment to measure the energy change when 50 cm³ of copper sulfate reacts with 10 grams of iron. And use a polystyrene cup to minimize heat loss, and add copper sulfate solution into the cup and then measure the temperature of it, and add iron into the cup and measure the temperature increase of the solution, and take readings every 30 seconds in order to plot a graph. So the reason why we have this polystyrene cup instead of just a beaker is to minimize heat loss, because polystyrene cup is an insulator of heat. And here's the equation just to remind you. Then we have some limiting reagent versus excess reagent. So this thing right here is a substance that is in excess, and it's the opposite, substance that is limited for this. And this is how to determine if it's in excess or limiting. If the given moles in the test is less than the moles that it should be, it is limiting. Let's say if the question gives you NaCl is 2 moles, but the given mole is less than the actual mole, it's limiting. So it's quite a complicated process or concept, so I'll just rewind this again. If the given moles is less than the moles that it should be, it's limiting. Let's say the moles of NaCl is let's say 10 moles, but the question only gives you 8 moles of NaCl. That means that NaCl it's limiting. And here's to find it and some examples. And then we have Extrapolate displacement graph. We have this displacement graph over here. and some points. And then here you just draw a line for the temperature change to the peak, like here, and then draw a line of best fit to see where it meets, and it reaches, to find out the temperature increase and the peak temperature. And then we'll look into calculate enthalpy, and as I talked about just now, enthalpy is joules per mole. So basically you just find out the Q, or the energy or the heat release, and divide it by the moles of that substance, because enthalpy is joules per moles. And then we'll move on to delta H and bond energies for energy profile diagram. And here's some questions. Excess magnesium powder is added to 30 cm³ of 2 mole solution of sulfuric acid, and the temperature increases from 22 degrees Celsius to a maximum of 50 degrees Celsius. So this graph is kind of incorrect because the activation energy will only be half over here, because activation energy is from the peak to the reactants, and the reactants to the products will be the energy released. So you see it's going down because it's exothermic. Then here's more questions. The energy change for dissolving ammonium nitrate, this plus 25 kilojoules mole, so no, it's positive, so it's endothermic. And the sample of ammonium nitrate is dissolved into 500 cm³ of water, and the temperature falls by 50 K. So you know that it's endothermic, and the activation energy, and the energy absorbed, or the energy absorbed. Oh, sorry. So it's positive delta H because it's endothermic. So we'll move on now to a neutralization graph. So basically you can see this curve over here, and this, you just draw 2 lines of best fit for the curve at its peak to find where it intercepts, to find the volume of titrant where it is neutralized, and the temperature. Then here's some strong acid information. In an energy profile diagram, if a hydrochloric acid is used instead of sulfuric acid, the activation energy will stay the same because you don't know the activation energy, but the reaction will be less exothermic because hydrochloric acid only has one H. Let's see, hydrochloric HCl and H2SO4. So the red is HCl and the black is H2SO4. Because the H2SO4 has 2 hydrogen, and the red, which is hydrochloric acid, only has 1 hydrogen, that means that the black, which is H2SO4, will react more because it has 2 hydrogens to react for every mole. So it will be more exothermic. Then we have some questions. So here's some question over here, and here's a graph. You can see, you just draw the line. Because we know that this 4 value is missing due to a spike in the temperature, so draw a line up and see where it intercepts. And then we have some questions. You can have a read using the graph. Just go back to the timestamp just now to see the questions for some reference. Then we'll move on to endothermic and exothermic for bond energies. Endothermic is taking heat and energy into breaking bonds, and the closer to the gas state, they have more energy. And thermal decomposition is an example of endothermic energy. An exothermic reaction is release heat and energy to make bonds, and they're closer to the solid state as they have less energy. So here's bond energies. The typical bond energy question would be like this. So they will give you like a reaction. It will either draw it out or write some the chemical equation. So if they draw it out, it's much more clearer to see. So on the left hand side, which is the reactant, it will be endothermic side over here, and on the product, it will be the exothermic side. So here's the table that they give you to look into the energy in each bond. And so let's say in the endothermic side, right? Calculate how many OH bonds there are. There's 1, 2, 3, and 4. So OH bond, what's OH bond? OH bond is 464 energy for kilojoules. So OH will be 4, and 4 times 464, because that's the total amount of energy on the bonds for the OH bond. And for the O bonds, there's 1, 2, so 2 O to O bonds, and O to O is 146. So 2 times 146, and the endothermic will be 2148 positive. And the exothermic, you can see 1 double O bond, 498, 498, and it's negative because it's exothermic, remember. And for the rest, it's just OH at 1, 2, 3, 4. So 4 OH bonds, and OH is 464. So 4 times minus 464 equals minus 2354. Just add them up together. And then the energy will be just this, the endothermic plus exothermic. And in this case, it will be 2148 minus 235 plus minus 2354 equals minus 206. And the total reaction has a negative enthalpy change. Hence, this reaction is an exothermic reaction. And here's more questions you can have a read. Like this. And like this. So this is an A-level question, so just skip this if you don't understand. But if you still don't understand, I'll just explain it one more time with this new example. We have this right here, CH3COCH. Right here, sorry, COCH3, not COOCH, sorry. And this structural formula, plus 4O2 equals 3CO2 plus 3H2O. And for endothermic, it's this side because it's the reactant. So calculate all the bonds there. You draw out it's better to draw out the structure like this. Structure. It will be CH and stuff. So there's 6 CH bonds, and 2 CC bonds, and 1 C2O bond, and 4 double O bonds because there's 4 over here. And then just calculate the respective mean bond energy or the enthalpy. So 6 times 412 because CH is 412. 2 times 348 because there's 2 C to C, 348. 1 times 804 because there's C2O is 804, and this. And exothermic, you can just draw out the structure, and there's 6 CO bond and 6 OH bond. So it's this times this, it's negative, and this times this, and it's negative. So you get this, and the total energy is just 5957 plus minus 7608 to get minus 1651. So the total reaction has a negative enthalpy change. That means this reaction is an exothermic reaction. And that's the A-level question as I talked about just now, but you can have a read. And that's it for this lesson of IGCSE Chemistry, and I hope you guys have enjoyed this, and please leave a like and subscribe and comment down below if you've enjoyed it or if you have any criticisms and any questions. And also check out my Instagram in the description for more daily content, and email me, and my email is in the YouTube bio if you have any questions or any requests. So I hope you guys have enjoyed this, and I'll see you guys in the next lesson for chemistry or any other subjects. But until then, stay safe and happy learning.